Good morning, my dear students. Welcome to this session on cables and suspension bridges. So, till the last session, we have discussed about the cables subjected to point loads. Okay, so now let's move on to this cable subjected to uniformly distributed loads. Okay, so we have seen the examples for cable subjected to single point load and 2 point loads and then multiple point loads. Then cable having the supports at the same level, same elevation, then supports at different elevation. So this is all what we have seen, right? We have solved the examples, and also some unsolved problems are also being told to you to practice. Okay, right, now let us see how you solve for the unknowns in the system where cable is subjected to uniformly distributed load, and how it is different from the earlier solution. Okay, so what happens when the cable is subjected to UDL? Right, so the cable is going to deflect in the form of a curve. Okay, what happens when the cable is subjected to a point load? Okay, so if this is a cable, if it is subjected to a point load or number of point loads, what is going to happen to the cable? It is going to deform in the form of so many straight lines. So that's a basic difference that you have to understand. So whenever a cable is subjected to point load, okay, whenever a cable is subjected to point load, the cable is going to deform in the form of straight lines. So it is enough if you find the sag value at the load point. So if you know this sag value at this point, you can calculate sag values anywhere you want. Okay, because it is linearly related. Whereas here, the cable subjected to UDL is going to deform in the form of a curve. Okay, so if you know this value or somewhere the sag value, to find value at other locations, the simple linear relation is not sufficient. So you should know that what is the nature of this curve. Then only it is possible. Means what? If you have an equation for this curve, okay, so if I say this is some y value, so at some distance x. So if you know this equation of this line curvature in terms of y is equal to some equation, then if you substitute x is equal to some 1 meter or 2 meters or something, then you will get y value at that point. So that is the requirement here. Then obviously the tensile force at each point is different. This point tensile force is different. At that point tensile force is different. Okay. Whereas in case of cable subjected to point load, tensile force is same in a particular segment. So throughout the segment, tensile force is constant. Similarly, throughout this segment, tensile force is constant. right? Whereas here you see the tensile force is going to change at each and every point. So you have infinity values of tensile forces in this cable. Got it? So then what you want from this? So we don't want all those tensile force values. Okay. So we may need some maximum values or minimum values for that matter. So that is what is required. Got it? So here, why we are not solving for all the tensile force values, because they are infinity in number. You can't solve all those values, right? Whereas when you compare this with point loads, you have only limited number of tensile forces, maybe three, maybe four, or maybe five. Okay. So whereas here there are infinity number of tensile forces. So that's why, because what? There is now between the, say if you have a point load here, right? So the tensile force between this load and this load is constant. Tensile force between this load and this load is constant. Whereas you have load everywhere. That's why this point you have a vertical load, whereas very next point you have a vertical load. So the UDL is like infinity number of point loads if you think of like that. So you have infinity number of tensile forces. So at each and every point the tensile force is different. Okay, so all these points you have different tensile forces. So that's why we need only maximum and minimum values, not all. Now you got my point. So what we need from a cable subjected to UDL, we need what is the equation of the deflected cable, equation for deflected cable we want, because if you want to know the sag value at some particular point, when you substitute x value where you want the sag value, you will get sag value, right? So when it is possible, if you have the equation for this line, okay. And other requirement, what do you want is the maximum or minimum tensile force in the cable. Got it? Maximum tensile force, minimum tensile force in the cable. All other values we don't want. Okay. So for that, what we need? So we apply cable theorem for this case of UDL, cable subjected to UDL. So we have studied the general cable theorem, right? What is that? At any point on the cable, horizontal component of tension in the cable multiplied by the sag value of that point is equal to bending moment at the same point on a simply supported beam having same span and same load. Okay, so that is the cable theorem. So left hand side I have product of horizontal component of tension, that is H, and Y is the sag value. Okay, is equal to, this is bending moment when you assume that there is a simply supported beam of same span, same load. This is the bending moment in the this equation you remember, I think we have derived this to prove the theorem. We have this expression, right? So sum of all moments about B multiplied by X by L minus sum of all moments about the point where you want the y value, where you are taking the y value, right? So this is the right hand side. Now you apply this theorem to this case of a cable subjected to UDL. Okay, right. So x by L, sum of all moments about B, you substitute it here. So take moments about B. Okay, so you assume a simply supported beam with UDL. So sum of all moments about B, I'll just show you that how this will be. So this is the problem. So there is UDL, this is L, this is A, B. So if you take moments about B, right? What do you say? Sum of all moments about B. Okay. So what you have there? So this is point B. So this is W L by 2 is the reaction, right? Total load, what is total load value? W into L is the total load value. So half of the value is the one reaction, WL by 2. So if you take moments about B, RA, that is WL by 2 into L. W L by 2 into L. Okay, clockwise, either clockwise positive or anti-clockwise positive, whichever is the value that you take. Minus W into UDL. L into L by 2. Distance L by 2. Okay. So that is sigma MB, okay, into X by L. So in both the cases, you are getting WL square by 2. So MB is 0, right? Sigma MB is equal to 0. So that we are proving WL square by 2. Okay. Right. So got it? Sigma MB, right? Only due to the loads. That means WL square by 2. So this is from reaction, this is from load, right? So this is only from the loads. Okay, if you remember that what is sigma MB, I'll show you. So to prove the cable theorem, how you write this, what do you mean by sigma MB? Right, see this is the one which we wrote, sigma MB by L into X by L. So what is sigma MB? See, at moment equilibrium about B is taken. So right hand side you wrote sigma MB VA into L plus H into L into tan alpha is equal to sigma MB. This is for cable you are writing, okay? VA into L, H into L tan alpha, H into L tan alpha. You are taking moments about B, right? So for all these forces, P1 into X1, P2 into X2, P3 into X4, X3, P4 into X4. For all these, I just put a notation here, okay? So that is what is sigma MB. So don't misunderstand. This is sum of moments about B for applied loads only. So that I would like to tell you, and we apply the same here. Okay, right, got it. So now take moments about B for only the loads applied. So only one load is there, UDL. So that is WL square by 2 minus. So take some section X. So sum of all moments about x only due to loads, right? Only due to loads means what? So if you take a section here, x so w into x by 2, x by 2. Okay, so w x square by 2. So what is happening here? So L, one L goes, okay. So W x by 2 is common, L minus x is remaining here. So W L by 2 and into x is remaining, W x square by 2. So W into x by 2 is taken common. Here also x into x if you write. So Wx by 2, Wx by 2. Both in both the terms it is there. So what is remaining? L and x. So L minus x. Okay. So this is from the cable theorem. Remember once again, sigma mb means sum of moments about b for only due to applied loads. Similarly, sigma mx means sum of all moments about section x only from applied loads. Okay, right. Now apply cable theorem at point C. So this is the point that is selected. So apply cable theorem at this point. Right. So cable theorem, if you want to apply, what do you need to do? H into y, okay, is equal to h into y is equal to right hand side sum of all moments about this point only due to loads. Okay, only due to loads, right? So if you take a section here, w into span is L by 2 load span, and the distance is half of L by 2. That means L by 4. So how much you get? WL square by 8. Moment at center. So what is Y at center? H. So substitute Y is equal to H. So horizontal component of cable tension at C is equal to WL square by 8H. Okay. Horizontal component of cable tension. Okay. That means the horizontal component of tensile force at this point H. Okay. Value WL square by 8H. Right. Now y is equal to from the expression, earlier expression. So this is the expression that you are taking. So from that, what is y? Equation for y is equal to wx by 2h into L minus x. Okay. Now substitute the value of h. Okay. Right. So what is that? Just now we have calculated WL square by 8h. So substitute that. So what you get? 8h goes to numerator, WL square in the denominator. Okay. So W goes here, L square remains 2 fours. So 4 times Hx by L square into L minus x. So what is this equation? We have seen this equation earlier also. So 4hx by L square into L minus x is the equation for parabola. Okay. So what does this mean? That the deflected shape of a cable when UDL is acting, it will be parabolic. The shape of the cable, deflected shape of the cable is parabolic. Okay, right. So to do that, what we have done, we have applied the cable theorem for the cable at some section X. We got this expression. Then we have applied the same theorem at the C. Then we have got H value. Then we have substituted this H value into this one to get what is Y equation for the deflected shape. Okay, so we got that it is a parabola. Okay, now another quantities that we want are the tensile force in the cable, right? So take a section anywhere in the cable. So I have cut the cable at this point, let us say. So the force will act in the cable perpendicular to this section. So that is this. So the same is shown here. If you take a section at this point, okay, so this 90-degree. Now to calculate tension in the cable, this is what we want, right? So T cos theta. See, this is the right hand support. So horizontal reaction, vertical reaction. Free body diagram of the part of the cable. So this part of the cable is removed. Now you see there is UDL, this portion. So the selected portion is having X span and Y is the vertical distance between that horizontal line and the point selected. So there are two components for T here. This is horizontal T cos theta, T sin theta. Okay. So T cos theta sigma fx 0 if you see. So this is horizontal force and this horizontal force. So T cos theta minus h is equal to 0. So T cos theta is equal to h. So what is T is equal to h by cos theta. So h divided by what is cos theta. Okay. So if you just see that if you take a portion of the cable, right? So this is dx, this is dy, and this is ds, length of the cable along the curvature. So this is theta with respect to horizontal, the inclined line with respect to horizontal, this is theta. So what is cos theta from this triangle? Dx by ds. That's why it is written like this. Okay. So what is ds again? ds goes to numerator, right? What is ds? Square root of ds is equal to square root of dx square plus dy square. Okay. Right, that is substituted in terms of ds. So now take dx outside. So dx square comes out. So here there is no dx square. So what you do? Multiply with dx square divided by dx square. So now dx square will come out of the square root and will become dx, and denominator dx, numerator dx will cancel. Okay, so this is came out. So there is 1 here, and dx square is gone, numerator 1. So dy by dx whole square is remaining. Okay, right. What is dy by dx? You have y is equal to 4hx square, 4hx by L square to L minus x. Parabolic equation, right? So now you do dy by dx for this. This dy by dx for this. Okay. So 4h by L. Okay. Or just leave the quantities which you can cancel out into. Okay. Uh, L you can keep it inside. Okay. If you want, you can take it out, but just so x is now I am now sending x inside. So inside x into L is there. So dy dx of xl is L. Dy dx of x will be 1. So L will remain inside minus x gone inside. So became x square. So differentiation 2x. So this is how we are performing dy by dx. So 4h by L square to L minus 2x. Now you substitute this into this equation. This is what is equation for t. Okay. So h into square root of 1 plus dy by dx whole square. Whole square of this 16h square by L power 4 L minus 2x whole square. Okay. So this is equation for T. Tensile force at any x distance. You substitute any x value. X is 0, x is L, like that. Okay. So if you substitute x is equal to 0, what happens? This will become 0. So L square by L power 4 will be 1 by L square. So 1 plus 16h square by L square. So that is the maximum value. Okay, x is equal to 0 means what? Supports. Supports maximum tension. Now x is equal to L by 2 if you substitute. X is equal to L by 2. So 2 times L by 2 is L. L minus L 0. So total numerator 0 here. 0 by anything is 0. So square root of 1 is 1. So h will become T is equal to h, where midspan x is L by 2 means what? Midspan tensile force is h equal to h. Okay, so now you got it. So if you see the cable, so maximum tensile force in the cable occurs at the end, cable end. Okay, means support. So this is T maximum. This is T maximum, and this is T minimum. So minimum tension is always equal to H. So maximum tension is depending on the values of this H and VA. So T maximum is equal to square root of H square plus VA square. This is T maximum. Or you have a direct formula. So that also can be written like this. Okay, so T maximum h into square root of 1 plus 16h square by L square. Okay, so due to uniformly distributed load, cable takes parabolic shape, and that is this. All this is done by Galileo. Whereas due to its own weight, the cable takes a shape called catenary. So that is derived by Leibniz. Okay, so y is equal to the shape of the catenary is y is equal to a into cos x by a, right? Anyhow, we are neglecting the self weight. That's why we are neglecting. We don't get into this equation. Okay, so got it. So the cable applied by UDL along the span, there are two cases that you have to clearly understand. Okay, so the cable applied by UDL along the span, the shape of the deflected cable is parabola. Okay, whereas if you consider self weight of the cable, that will act along the cable, not along the span. Okay, see, this is the weight of the cable that is acting, not along the span, not along this horizontal line. This will act along this curved line. Okay, so that's why the deflected shape of the cable under its own weight is not parabola. Got it? Then what it is? It is called as a catenary. And what is the equation for it? Y is equal to A times cos hx by A. Okay. So there is a clear difference between these two. Both are looking like UDLs. So UDL acting along a horizontal line, the shape of the parabola is shape of the deflected shape of the cable is parabola. UDL acting along the cable line, the deflected shape of the cable is catenary. Okay, right? So this is the complete information regarding cables subjected to uniformly distributed loads. So when a cable is subjected to UDL along the span, so the equation for the deflected shape is parabola, and the tensile force equation for tensile force is h into square root of 1 plus 16 h square into L minus 2x whole square by L power 4, and maximum tensile force occurs at the supports, and the value is h into square root of 1 plus 16 h square by L square, and minimum tensile force will occur at mid-span, that is equal to horizontal reaction at the support. Okay, and there are two deflected forms that cable can have. One is parabola, another one is catenary. Parabola is the one which you get when UDL is acting along the span, When the catenary you get when the UDL is acting along the length of the cable length. Okay, right. So this is the complete information regarding cable subjected to UDL. Okay, so we'll come back to the next class, next session on an example problem with an example problem of cable subjected to UDL. Okay, right. Thank you.